off last time. So we've just finished the quiz, and this is class 13. We get through 41 during the semester, so we're definitely making progress. We're more than a quarter of the way there. Your next homework assignment is due a week from today. That's applying the Hardy-Cross method that we're going to finish up today. So I haven't put that onto Blackboard yet, but I'll do it after class and you'll have it available. We're going to finish that Hardy-Cross example that we didn't quite finalize in Monday's class, and then I have some additional Hazen Williams equation problems to share with you just to use up the rest of our time. Just to revisit this problem that we started on previously, this is showing after I did my flow balance. And remember that you probably had slightly different numbers for some of these pipes, and that's okay as long as we have in equals out at each junction. And I also told you it's best if we don't have any flow rates that are zero. You can, and it will eventually work, but it takes more iterations if you start off with some actual flow rate through each pipe. All right. Now, the template file that I gave you before is where we're going to revisit. I didn't have anybody stop by my office asking for help to get up to speed. Hopefully that means because everybody is on track, and if that's not the case, if you do need help, please stop by because I'm eager to help you understand this process. So what we did was we've already, in the first iteration, used the fully turbulent flow assumption for our F values. And then we calculated the R's based on this formula. And then we kind of went through the process of correcting our initial guesses of flow rates. Now, what did I tell you are the two most popular mistakes? Anybody recall what are the favorites when it comes to making mistakes in this method?
The signs change when you go from loop to loop.
Good. The signs change from loop to loop. So I've bolded CE and EF just as a reminder that those are in both loops. And so when I have an updated flow rate, then I need to make sure that I use the negative of the previously calculated flow rate. And so what you'll notice is that for CE and EF, rather than putting in my initial guess flow rate in our first iteration, I'm already using the latest and greatest flow rate estimate from the previous loop. So I don't start with just my initial flow balance. The initial flow balance for CE in loop 2 would have been negative 0.5. But I don't use the initial flow rate. I use the opposite of this previously calculated. So the previously calculated flow rate from the perspective of loop 1 is 0.603. From the perspective of loop 2, it's negative 0.603. Okay, so that was one of the most popular mistakes. Anybody remember the other one that I mentioned? Has to do with this equation. People just sometimes miss that minus sign. So when you're calculating the delta Q, make sure that you put the minus sign in for that. All right. So here's where we left off last time. We'd finished the first iteration, both loops, and we were about to start on iteration 2, loop 1, and you'll notice that the full Jane equation is used. So we're not just using the fully turbulent flow for these F values. We're utilizing these Reynolds numbers that were calculated in the previous step. And one thing I'll point out is CE. All right, that's one of those common pipes, the ones that's in both loop 1 and loop 2. Right now, the F value is calculated based on this Reynolds number, but do I have a more recent guess of the Reynolds number for that pipe? I do. So let me drag this down and have it reference this, because this is my most recent guess of the Reynolds number. And then the same thing is true of EF. Let's look at right now, this is the full Jane equation, but when it's asking for Reynolds number in the Jane equation, it's looking up here into loop 1, iteration 1. And do I have a more recent guess for pipe EF? I do. It is this Reynolds number. So I've improved my F value guesses slightly by making that adjustment. It still would eventually converge if I didn't make that adjustment. That's not a fatal mistake. It's just an improvement. There are certain things that have to be perfect. This is one of the few that the F values just converge faster if you use the most recent Reynolds number. All right, so N is just going to be 2 for all of them. So we can just enter in 2 because that's what's associated with the Darcy-Weisbach friction loss method. All right, so now, what flow rate should we use for AB? It's not our initial guess. That would be the ultimate foolishness, would just be start 0.5 because that's what my initial guess was. We're always asking, what's our previous guess? So our previous guess of the flow rate through AB is this corrected Q. All right, for BC, it's the corrected Q from the previous iteration. All right, CE, this is in bold. So it's going to be equals minus of the CE from loop 2, iteration 1. So I'm not just going to reference loop 1, iteration 1. I'm going to use loop 2, iteration 1, and the negative of that. Why negative? Because from the perspective of loop 2, the flow rate is clockwise. Well, from the perspective of loop 1 that's clockwise, in loop 2 it was counterclockwise. So that's why it was negative here. It needs to be positive there. Same thing for EF, equals minus of this most recent guess. Since it's in the other loop, I have to put the minus sign. And then AF, I'm just using the previous estimate of the corrected Q. Okay, now I want to calculate the RQ absolute value Q, N times R times absolute value Q. I want to calculate the delta Q, the corrected Q. You know, actually, I can just highlight all of this stuff, copy it with Control-C, and then paste it here, and it's going to do relative references and do all the calculations that I need. And what we hope to see is that the percent change is smaller in this block than it was in the previous. So look here. In iteration 1, it was 17% change for the guess flow rate compared to the corrected flow rate. So it's smaller than here where it's 3.2. Another indicator that things are getting better is look at the delta Q. In the first iteration, it was 0.1 cubic meters per second. Now it's 0.019. So the delta Q is getting smaller. That's also an indicator that things are headed in the right direction. All right, now let's set up. Sorry, guys. Let's set up this next loop. So the F values, we want to use the full version of the Jane equation. So let me just copy Control-C and Control-V, and I'm going to have to make sure that it's using the correct Reynolds number. So where's my best estimate of Reynolds number for pipe CE? It is this one. Okay, and let me drag this down and then just make sure where it's using, that's the correct EF Reynolds number. And then for CD, there's the correct reference to the Reynolds number for CD, and then let me drag that down for DF. So we have a next group of F values. Now once we've made that adjustment, everything will just be able to be copy and paste at this point. So let me copy all of this. No, I can't copy all of it because some of this is just typed in the original guess flow rate. So I have to be more judicious when it comes to the flow rate. So I can just copy like the calculating the R's and the N values. So Control-C and Control-V to copy and paste that. Okay, now for the flow rates. Okay, so what's my most recent CE? It's equals minus of this corrected Q from the previous loop in the same iteration. EF equals minus of the corrected Q in the same iteration. Okay, what's my best guess of CD? Equals, it's the previous corrected Q here. And then DF, my best DF guess is there. All right, now that I've referenced the correct flow rates, I can copy and paste all of this from the previous iteration. Control C, and then get down into the right spot where I want it to be pasted and click Control V. And what are we looking for? We're looking, is the delta Q smaller than the previous delta Q? So in the previous iteration, the delta Q was 0.18. In this, it's 0.02. So we have a dramatic reduction in the correction factor, which is a good sign. The percent change is getting smaller, which is a good sign. I'm going to zoom out just so that we see the whole solution all at once. Now, what I can do at this point is really fast. All the previous iterations, I can select the whole block, the entire iteration like that. And since at this point everything is relative references, I can just copy and paste below it. Once I Control C to copy, and then just select the immediate cell beneath that block and paste it, Control V. The only thing I need to change is I just need to call that, instead of 2, this is iteration 3. So I've just changed that one cell just as a label. And then let's see, is the delta Q getting smaller? Yeah, the delta Q continues to get smaller. The percent change is getting smaller. Now the exception to that is BC. See how BC still has an 18% change from the inflow to the outflow? The thing is there's just very little flow going through pipe BC, and so it's going to take some extra iterations to get convergence in pipe BC. But that's not a problem. That's just the way it is. So let me now do a fourth iteration, select all of this, and copy and paste. And now the percent changes are really small at this point. We can consider this converged, because if you look at the flow rate for pipe BC, it's saying 0.019 is the initial guess flow rate, and the output guess 0.019. So because the delta Q is so small, you know, it's not even 1,000th of a cubic meter per second. It's not having any effective changes anymore. So we can consider this solution converged. And the way that you could check it is, you know, does flow in equal flow out at each pipe? We need to double check that. Here's the flow rates that it comes up with. You know, in this sketch down at the bottom, it's got the final flow rates. So, for example, 0.419 down towards F, 0.581 over towards B. Those two together are equal to the 1 cubic meter per second that's coming in. So the same thing is true at every junction. The flow in equals the flow out. The F values aren't changing from iteration to iteration. If we look at the F values, you know, here is the F value in iteration 4. It's the same as the F value was in iteration 3. The F values have converged. Flow in equals flow out. The correction factor for the flow rates, the delta Q, is effectively 0. And the percent change is, in most cases, below 1%. Certainly, even for this low flow rate one, it's below 2%. So any questions so far? So now the second part of this example was, the first part was find the flow rate in each pipe, and we did that. So here are the flow rates. That's the flow rate in cubic meters per second for each of these pipes. The next part of it in the example was find the pressure at each node, assume level terrain. So each of the Z values is the same at every junction. We want to know how much pressure is there, because the pressure will be going down in the direction of flow, won't it? Like, look at point A. Point A is going to have the pressure of 600 kPa. 600 kPa at location A. So will the pressure at B be higher? No, it'll be lower. Otherwise, the water wouldn't flow from A to B. So there has to be a decrease in pressure from A to B, and that's why the flow is going towards B, is that's the location of lower head. So what we know at junction A is 600 kPa is the given pressure at location A. Now, how much head is that? Remember, the relationship between pressure head and pressure is that head is the pressure divided by gamma. Yeah. So if we divide the pressure here by 9.81 kilonewtons per cubic meter, then that gives us that there's 61.16 meters of head at location A. So that's how much head there is at A. There's going to be less head at B. How much less? Well, we've calculated, we can calculate the head loss due to pipe friction through each pipe. It's going to be, the head loss is R times Q to the power of N. See this formula here? Head loss is R times Q to the power of N. So what we could do is we could calculate the head loss through each pipe. Let's do it off to the side. Let's calculate that here. It is pipe H sub F in terms of meters. How much energy is lost through each one of these pipes? It is the R value, which is here, times the flow rate, which is this, to the power of N, which is 2 in the case of the Darcy-Weisbach friction method. So through pipe AB, we're losing 5.49 meters of head. So I can drag this down through all of the pipes, and it'll tell me how much head loss there is through each pipe. Okay, so how much head is there at B? At B, there is however much head there was at A minus the loss through AB. So we knew that there was a pressure of 600, which means a head of 61.162. Energy is being lost as the water flows from A to B in the amount of 3.49 meters. So the remaining head at B is 57.67 meters. All right, so now what about C? How much head there is at C? You'll notice here in the side it says it's the amount of head that there was at B plus the losses. Now why plus if, through this one we did minus the losses. Why is it that we're adding the losses as we go to C? It's because we're going against the flow direction. If the final flow direction is from C towards B, that means that there's more head at C. So we're trying to calculate how much head is there at C. It's the amount that there is at B plus some increment that is the flow, the head loss through BC. So plus this. And there's not a lot because there's very little flow rate going through there. Looks like it's a 1,000th of a meter. So the head is a little bit higher. So once we know the heads, then we can calculate the pressure by, it is the head multiplied by 9.81 kilonewtons per cubic meter. And that's going to allow us to calculate the pressure at each of these locations. So we need to find the head at D. That is the head at C plus the losses through pipe CD. So the head at C plus, here's the losses through CD there. E is the head at C. No, yeah, the head at C minus the losses through CE. And then finally at F, there's a couple of different ways we could do F. We could say it's the head at A minus the losses through AF, or we could say it's the head at E plus the losses through EF. And it would give us the same answer either way. So I've written it here as F plus the losses through EF. So I'll say it is, oh, it's not going to be the head at F. I meant the head at E. All right. So here at F, it is the head at E plus the losses through pipe EF. And then we multiply by 9.81, and now we have the pressure at every junction in the network. So what you should have right now is a fully functional, correct, converged Hardy-Cross spreadsheet template. And if you don't, please stop by my office so I can help you get one. You know, I can help you troubleshoot and find the mistakes and get you up to where you need, because you now have a week to do a couple of homework problems related to this, and you'll find it easier to solve those homework problems if you have a functional example as a starting point. Any questions before we move on? All right. Well, then we will leave that there for today. Here's the same solution that we were just looking at. All right, I have a couple of additional problems related